Hello everyone, and welcome to this video. I hope you're all well and things are as they should be for you. Now in this video, we're going to look at how the coordinate singularities of the Kerr metric in the region near the horizons, where delta equals 0, can be removed using the Advanced Eddington-Finkelstein coordinates. Now just briefly, in the Kerr spacetime, Eddington-Finkelstein coordinates are a set of coordinates used to describe the geometry of the black hole in a way that avoids coordinate singularities at the event horizon or horizons. These coordinates provide a useful way to study the behavior of particles and light near the black hole without encountering coordinate singularities. All right, so let's start. I suspect I'm probably going to have to remove that. Okay, so in Boyer-Lindquist coordinates, the Kerr line element is this. All right, and where mu is gm on c squared, delta set to 0 gives us the horizons, the event horizons both, and rho squared is this object here. Now, unlike the Schwarzschild geometry, the Kerr space-time is not spherically symmetric due to the effects of rotation. This means we can't expect to find radial null geodesics like those of the Schwarzschild space-time. Now, the Kerr metric does have axial symmetry. And we've seen that how angular momentum in the phi direction, that's in the azimuthal direction, is rotation about the vertical axis of rotation is conserved as a conserved quantity. So with the axial symmetry of the Kerr geometry, we can expect to find null geodesics that lie in the hypersurface ds squared equals 0 for null particles, and d theta d lambda set to 0. So for constant theta, we can find hypersurfaces that contain null geodesics. All right, next one. Using this this metric and Lagrangian, we built using this metric and a Lagrangian built from it in previous videos in this series. Particularly go back to the very early part of the geodesic series, we can find the equations from which the principal null geodesics can be found. Now these principal null geodesics occurred later, and for the life of me, I can't remember which video series that was in. But anyway, by anti-differentiating these gave us these geodesics here. Now these geodesics, these two were found, or the trajectories that specify the geodesics, were found in the videos numbers 14, 15, and 16 of this series. The plus here is the outgoing geodesic, and the minus is the ingoing. All right, now, and just as an example of these, let's plot the first two of these cases. That's the ingoing and outgoing geodesics in the CT in the TR plane, TR surface. As an example, let's plot the first hypersurface, I should say. The first two of these cases for a billion solar mass black hole with a dimensionless spin parameter A star is 0.8. Okay, so mu is gm on c squared, A is gm on c squared times A star. A star is the dimensionless spin parameter. It's going to be between 0 and 1. Here, mu squared is greater than A squared in these cases here. So we don't have a fast Kerr or any of those cases. All right, now, so the ingoing geodesics shown in red here, and the outgoing in blue. The outer event horizon R plus, the inner event horizon R minus, and the stationary limit surface, the edge of that is just outside the outer event horizon, just out along here somewhere, close by, but just outside. I'm not marking those in for this video. Now, we know in the Kerr line element that you have this term in the denominator in front of the dr squared coefficient where delta, and now delta equals 0 at the event horizon. So we have this singularity, which is not a physical singularity, it's just a coordinate one. It's just the choice of our coordinates. And by removing that, we can come up with geodesics which aren't limited by those coordinates. If you have a look here at these event horizons here, you can see how these geodesics asymptotically approach them, but they don't cross. when really we do expect that matter and energy will cross the event horizons and pass through. We do expect that, but the geodesics here in Boyer-Lindquist coordinates are not really showing that. What they're showing is that the massless particle, in this case here, asymptotically approaches the event horizon but doesn't cross it. Okay, so it's not unreasonable to expect that matter and energy do cross the event horizon. In this case, we're just dealing with null particles, but so energy. And so we seek coordinates, as we did in the Schwarzschild case, where we go from Boyer-Lindquist coordinates, tr theta phi, to advanced Eddington-Finkelstein coordinates, for the ingoing case, ct dash r theta phi dash. So r and theta don't change, but ct dash and phi dash do. Now these are the advanced Eddington-Finkelstein coordinates. And it's these that we see. What form are they going to take? All right, well, what we have here from earlier, the differential form of those geodesics and choosing ingoing with the negative here, they're easiest to work with. So we have CDT as a squared plus r squared on delta dr and d phi as minus a on delta dr. Now, in advanced Eddington-Finkelstein coordinates, we want the principal null trajectory of photons to be straight lines. So we seek a transformation of the form that CDT dash is equal to minus dr. Now, at the moment, we have CDT is this object here, but we want to, but this is definitely not linear looking, whereas this is very linear looking. If you look at this, dr dt dash is equal to minus c, which is what we want. We want photons going in, crossing the two coordinate singularities, the two event horizons, and continuing on. We also seek d theta d phi dash is 0. All right, remember these principal null geodesics that were found earlier, they were in the equatorial plane. So that was the restriction there. So we seek a transformation of the form c dt dash is minus dr. Okay, we don't want c dt dash to look like this. In a sense, we sort of want to straighten it out. So it turns out the transformation will be this. C dt dash is c dt, that's this object here, plus this bit added on. And the effect of adding on that bit there, okay, the effect of adding on that bit there acts to, so to speak, straighten the trajectory. And I'll show you what I mean by that in a moment on the next slide, but it acts to straighten out the trajectory. And then we will end up that this object here will in the end just become equal to minus dr. So in a sense, it has this effect of straightening the trajectory up. Let's have a look at that. Need some evidence for that. How is it I can say that? Well, let's have a look. Okay, so CDT dash is CDT plus this bit here. Well, CDT for the ingoing case, ingoing principal null geodesic, or geodesics, minus a squared plus r squared on delta dr plus 2 mu r on delta dr. Okay, common denominator here, take out the factor of dr, common denominator here delta, and so we have a squared plus r squared minus 2 mu r on delta. Now, the numerator here, if you just look at that, that's the definition of delta. So what you have is delta on delta, minus here, of course, is the ingoing trajectory. Delta on delta cancel, we're left with minus dr. So c dt dash is minus dr. So this transformation here sort of straightens out the trajectories. Okay, it really it compresses the time component. It's like an infinite compression of the time component and straightens everything out. So instead of that asymptotic behavior we saw in the previous graphs for that billion solar mass example a couple of slides ago, it will straighten that out, do a compression and straighten them out. Okay, so that's what I mean by straightening. Another one is d phi dash. Remember how we wanted that to be 0? Well, just take the original d phi and add on a on delta dr, because remember that before was minus a on dr. So d phi dash becomes d phi plus a on delta dr, because remember this is in the equatorial plane, and we're fixing it there. So we're setting all the others to 0. You'll see why later in the video. D phi dash becomes then d phi plus this bit here, and this acts to untwist the space-time. So we have this transformation that untwists the space-time in the phi direction. Remember how due to the rotation, the frame dragging effect, where space-time itself is dragged around, curved and twisted around due to the rotation. We need to untwist that. Okay, so to do that, that d phi dash is d phi plus a on delta dr. Well, remember d phi was minus a on delta dr, and then adding the same quantity on gives us d phi dash is 0. So there's no, so in this trajectory, if it's coming in a straight line, we don't want theta varying and we don't want phi varying. We want a straight line coming in. That's what we're aiming at. The question is, can we do that? It doesn't mean nature behaves that way, but can we do that? Okay, it's reasonable to think that matter and energy cross, or in this case just energy, massless particles, crosses the event horizons on a straight line trajectory. It's not unreasonable, but can we get coordinates that give us that show us that? And we can. Okay, so the next steps are CDT dash is that. So that implies that just rearranging that, transposing it, CDT is this, CDT dash minus that. D phi dash was that, so that implies that d phi is d phi dash minus this. And then what we'll do is we'll put that into the Boyer-Lindquist line element. So we'll also do the square of that, expanding that gives us this, the square of that, expanding that gives us this. Now we substitute into the line element. Okay, so we end up with this. Here's our Boyer-Lindquist line element, our Kerr line element in Boyer-Lindquist coordinates, I should say. Here we are. Okay, and substituting that in, so c dt squared is in here, dt d phi there in the new coordinates. Okay, here we go, and this bit on the end. Okay, now next bit down, I want to expand out the last bit as well. I think that's the only change I made there is expand out this bit here. Here we go, next line down, and expanding all that out, we get all this. Well, I don't need to go through term by term, but you can pause the video and stop and check them if you wish. And as we do that, now we want to collect coefficients for like terms. So we have CDT-dr, collect all those terms. We have this object here. For the coefficients of dr squared, wow, got all this. Then dr d phi dash is this here. D phi dash looks like the original form, so does d theta. Dt d phi in here, okay. Now, we could do a lot of algebra to simplify this. You could spend a lot of time doing that if you want, but it turns out there's a quicker, shorter way of getting there, other than going through all the different combinations of putting deltas in here and cos squared down here, and especially down with this one too. You know, there's many different directions you can head off into, and it feels like you end up in cul-de-sacs. But there's a better way, a quicker way. All right, so we have all this here, again, collected all this. Now, to simplify these, what we can do is, I mean, you could spend all the time and doing the algebra, and even with a computer algebra system, they're going to take you off in different directions and give you something which is still quite large or unwieldy, but there is a better, more optimal way of doing it, and that's what I want to show you now. So the algebra can become quite involved here, but there is another quicker way. And what we do is we choose a few values of the theta here, okay, like 0, pi on 2, pi on 4, pi on 3, something like that, and then look at the pattern. So it's a bit of an inductive type method. So let me show you just with this one. I won't do the others, although I use the same method for all of them. I check them all. So we'll go next slide over, and we want to find the simplest form for this. Okay, so here we go. This is the thing we want to simplify. Let's try theta as 0. So I put theta as 0 in there. Well, that disappears. Theta is 0 in there. Remember, rho squared is r squared plus a squared times cos squared theta. If I put theta as 0 in there, well, cos squared theta is 1. And so I have r squared plus a squared underneath. And on the top, this bit will go to 0. This whole second term drops off here. You have 4r mu, so you get this format here. Now I can just build that back a little bit, which suggests that we have 4 mu r squared plus a squared cos squared 0. And which is really suggesting that this is really just 4 mu r on rho squared. Okay, we've got to keep checking. We need a few values to be sure. So try theta is pi on 4. 8r mu on this object here, which can be had from 4 mu's r, r squared o squared cos squared of pi on 4. And again, that looks like 4 mu r on rho squared. Theta's pi on 3 gives us 16r mu over 4r squared o squared, which looks like this, which is this. So in other words, if I take 4 mu r over rho squared and I put theta is pi on 3 in here, I just come back to this object here, which is really just this, or theta equals pi on 3. Theta is pi on 2. Right, we're now in the equatorial plane, gives us 4 mu on r, which can be had from this, or mu on rho squared for theta on, for pi on 2 for theta, just becomes r squared. 4 mu on r squared is 4 mu r on r squared is just 4 mu r. In other words, the pattern that we're seeing being induced here is that this object is this. Okay, that's all it turns out to be. All right, now we can do the same with all the others. I'm not doing that here. I'm not going to take up your time with that, but you can do it yourselves if you want. Okay, so using the above method gives us a new line element. And in this form here, we've made our substitution now where we've remember CT T dash and phi dash, and by doing that we've straightened and untwisted the space-time there, and so the geodesics will move now in a straight line inwards for the inward trajectory. Now what we do, just as we did in the Schwarzschild case, we define the advanced time coordinate u to be ct dash dot plus r, plus r. Now in differential form, this is du equals c dt dash plus dr equals 0. We know that to be the case. How do we know that to be the case? Because we had c dt dash is minus dr. So we get du is c dt dash plus dr. C dt dash we know to be minus dr plus dr is 0. So we know that du, this advanced time parameter, is also 0. Okay, so let's now put in where we see c dt dash. That will now be u minus r, or du minus dr, and we'll substitute that in. So I haven't actually put those couple of steps in, but you can see from here du is c dt dash plus dr. So c dt dash is going to be du minus dr. Okay, and then we'll put that in here in the line element. Okay, so we now have the line element containing our advanced time coordinate, and in it goes there. And that's our new line element, and then we can expand that and tidy it up. I'm just repeating the same again. The line element at the bottom of the last slide, this is it again, and we'll expand it all out. All right. Next thing we'll do is we'll collect terms, like terms, and we have this here, du plus this. Remember on this channel I use the -1 plus 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 signature. Some textbooks use the other signature, which is +1 minus 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 1. Okay, so just be aware of that. Now what we want to do, remember we're in the equatorial plane, so we set d theta, d phi dash to 0. So d theta and d phi dash will set to 0, d phi dash to 0, d phi dash to 0. Okay, we want these straight lines. We don't want any change in the angular direction in the polar or azimuthal direction, so hence d theta, d phi dash is 0. Null particle for photons, ds squared is 0. That'll go in there. Let's have a look at what we get next. So here's our line element again in advanced Finkelstein coordinates. Now we apply the conditions ds squared is 0 and d theta, d phi dash is 0. Remember, we don't want any twisting or bending of lines and so on. And this gives us this here. So there is a coordinate system which we can straighten out, the geodesics, in which, and we move those coordinate singularities, which are not physical singularities, they're just coordinate singularities. It allows energy or photons to cross straight over, all right, to pass straight through, as we would expect. Doesn't mean they do, but we would expect that. All right, so set that to 0. So solving that through, taking a factor du dr, tells us one integral. First integral is du dr 0, so u is a constant, first one. And then du dr is this object here, and we've seen going back to videos, I think numbers 13 and before, I think, in the geodesic series, and we looked at integrals like this. Okay, but which gave us these sorts of geodesics here. All right, so we only need the first of these two. Du dr is 0, u is constant. Okay, so as you can see, this is now the equation of a straight line. So from earlier, advanced time coordinate parameters, u is ct dash plus r. So our ingoing geodesics are given by ct dash equals minus r plus a constant. And then the second one gave us these. We'll pick now the outgoing geodesic. We only need the ingoing one here because we're interested in matter going in. We'll use the outgoing geodesics derived earlier in previous videos to tell us something about the light cones at different points in the space-time, which you'll see in the diagram shortly. So this form here came from videos 14 and 15 in this series. Okay, now, why use that one? You'll see shortly with the plot. But we've got now our straight line. This is an inward going geodesic, C minus R, inward going, and that's carrying our photons. These are the geodesics along which our photons are traveling, crossing the event horizons, as you'll see shortly. So let's plot the ingoing, outgoing geodesics. All right, now, right down here. Okay, now, so here we've got here CT dash R, and we've plotted the outgoing geodesics are these, I had them in blue, yes, so it's not really showing up here, but in blue, they're going out, so the blue ones, the wavy lines. These straight red lines are the ingoing geodesics, in the Eddington-Finkelstein coordinates. Here's our ingoing, crossing right over, not moving, curving asymptotically as they approach, or going out, or asymptotically approaching the event horizons. They're just crossing straight over them as though they weren't there, just passing, carrying photons straight through. Okay, now label this out here, region 1, which is time-like with a condition, region 2, region 3. Now region 1 is time-like up to the stationary limit surface, which is not shown here, RS plus, past which it becomes space-like. Now the stationary limit surface is about 2 mu along here, 2 gm on c squared. For this example here, I've used a billion solar mass black hole with a dimensional spin parameter of 0.8, and so this will be about 1.6 mu, or 1.6 times gm on c squared, and 2 gm on c squared out here somewhere is the edge of the stationary limit surface. At that edge, maybe a little bit further out, at that edge, the region from that edge in becomes space-like, right? So it becomes space-like. Regions 2 and 3 are space-like, so G00, the time component, the line element there at the front, it becomes positive, okay? And this becomes, they're all space-like. But really the space-like region starts out here in region 1, just at the stationary limit surface, just inside that. On the stationary limit surface, G00 is 0, and just inside that, as it crosses, the time-like component becomes space-like. All right, so that becomes space-like region from there in all the way to the ring singularity. Now, region 3, so space-like, and just a little bit here is space-like as well. At the ring singularity, which lies in region 3, you also have within the ring singularity, which is outside this diagram here, if you like, because it's in less than R0 in that negative range of coordinate R there, you have closed time-like curves, if they exist, where it's possible to follow time-like trajectories that do not end at the singularity. Now, from the stationary limit surface here somewhere in this, the light cones tip over, and they tip over pointing inwards. Right? In the stationary limit surface, they tip over, but it's not absolutely fixed that a particle must then cross the event horizon. So they don't all point into the event horizon there, but certainly in regions 2 and 3, they point inwards towards the ring singularity. But and so they tip over. So the future of any particle is towards that singularity. But this light cone here is trying to show you something. It's actually, I can't fit it to the left of the diagram because it doesn't make sense. You wouldn't know what I was doing. It doesn't make sense for me to draw it here. But at that ring singularity there, you do have a time-like region. And the time component of the metric goes negative again, at least for my signature. And so you have closed time-like curves. So a particle can avoid the singularity in that region there. That's just something to be aware of there. All right, so here again, just showing, note that the region inside the inner event horizon, R minus, that's region 3 here, near left of R less than 0, which I can't show here, not in a sensible way anyway, contains light cones that do not point at the singularity. This means there are geodesics that do not end at the singularity. All right, so in region 3 here, the light cones do tip over, pointing towards the singularity. But at the singularity itself, as you've seen in the whole causation and closed time-like curve series I've got on this channel, you'll see that in that region there, closed time-like curves exist where an object can avoid the singularity. All right, I think I've done everything there is. I think that's really about it. Thank you very much for watching this video. I hope it's helpful to you. I'll see you in the next video. Take care. Have a good day. Enjoy yourselves, and I'll see you in the next video. All right. Thank you, everyone. Bye.